Hi guys, welcome back to 7 Steps to a 7 in Olympiad number theory. In the last few videos, we were exploring what happens when we take a number n and prime factorize it, so p1 to the e1, p2 to the e2, so on and so forth. And usually for our purposes in the last few videos, we only ever had to take the problem mod p1 or mod p2 or modulo just individual primes. We never had to turn to these exponents over here. And this begs the question, what if looking at only mod p1 or mod p2 is not enough? How can we deal with these exponents? Then we need a clean way to deal with these prime powers, since if we try using arbitrary prime powers, then modular arithmetic can get very messy very quickly. For example, if I want to take mod p1 to the 3, p2 to the 4, p3 to the 5, and so on and so forth, then we have to look at each of these guys on their own, and it will become a huge mess. So we need a clean way to deal with these. And to do this, let's introduce the prime exponent function. So let me go and erase this. And let's discuss the prime exponent function. Okay, so what exactly is this prime exponent function? Well, as the name suggests, if you have a number n and a prime p, then it returns the exponent of p in this n here. So in other words, if you have, like, suppose n equals 2 cubed and p equals 2, then we end up outputting 3 because that's the number here. And we denote this prime exponent function here by nu p of n. This looks a lot like a v here, but it's actually the Greek letter nu. And this is also known in more technical terms as the p-adic valuation. Okay, so let's see some examples of the p-adic valuation in play. So first, I want you to see why n equals 2 to the v2 of n, or nu 2 of n, times 3 to the nu 3 of n, times 5 to the nu 5 of n, times 7 to the nu 7 of n, so on and so forth. And here we're going over every single prime. And your goal is to figure out why this happens. Because if you figure out why this happens, then that means that you probably understand the notion of nu p reasonably well for our purposes and know how it's used. Anyways, so now let's consider some more specific examples. So 1. Let's consider the number 2 to the power of 12. And we have p equals 2. Then nu p of 2 to the 12, I'll call this nu 2, and 2 to the 12. This is equal to 12 because that's the exponent over here. Okay, and now let's look at a smaller number. And let's go a bit smaller with the number 18. And let's look at p equals 3. Then we know that 18 here is equal to 3 squared times 2. So nu 3 of 18 is equal to, we circle the 2 here, and therefore it's 2. Okay. Then we have our third example, which is where we combine these two. So it is 4096, which is this up here, times 18. What is the nu 2 and nu 3 of this? Well, we can write this as 2 to the 12, and this as 3 squared times 2. So if we end up multiplying these two, we know that these 2 to the 12 and 2 will combine into 2 to the 13, and therefore we have nu 2 of this number is equal to 13 because it's up here. And likewise, when we have 3, for the new 3, we multiply the 3 squared over here with the 3 to the 0 over here. So that becomes 3 squared. And therefore, new 3 of 4096 times 18 is equal to 2, because that's the exponent of the 3. So hopefully you've had the chance to understand what the notion of a p-adic valuation is, the new p function here. If not, then I honestly don't blame you, because it's just something that you have to get used to. By the end of this video, you'll have plenty of practice with this thing here, and you should be pretty comfortable using it. All right, so with that said, let's go ahead and look at something else. Now, if this function nu p of n gives you some sort of deja vu where we added the exponents together when we multiply them, for example, nu 2 of 4096 times 18 was just 12 plus 1 as we calculated earlier. If this gives you some deja vu, then you're not alone, don't worry. And this is because from the definition, the nu p of n is greatly similar to the logarithm function, log of n, which we all know and love from our pre-calculus class. And after all, both functions allow us to single out the exponent and perform arithmetic with it. So in this case, we singled out the 2 to the 12 here and the 2 to the 1 here. And we added them together and singled them out. And similarly, what we do in log n is we take the base, so 10 to the n, or if n equals 10 to the k, then we just single out the k. And this is k. The point is that nu p and the logarithm are super similar. So with this, we can conjure some very basic nu p properties. And the first key property about logarithms that we know and love is that the log of mn is equal to the log of m plus the log of n. And does the same thing hold for nu p? Well, yes, it does. And by this intuition, you would expect it to be true. So we have our property 1, and it is nu p of mn is equal to nu p of m plus nu p of n. Okay, so how exactly do you prove this? Well, suppose that p to the nu p of m is the highest prime power dividing m. So this is basically the exponent of p and the prime factorization of m. And likewise, we have nu p of n is the highest power of p dividing n. It is the exponent of p in here. Then what is the highest exponent of p dividing mn? Well, it would just be the product of these two, because we're not going to get an extra factor of p from nowhere. So therefore, it's going to be p to the nu p of m times p to the nu p of n. And with this, the result just follows by combining the exponents. And by combining the exponents, we get nu p m plus nu p n is equal to nu p m n. And notice that this combining the two exponents here should make the resemblance to log clear, because in a way, log is just inverse exponential, and 10 to the x plus y is 10 to the x, 10 to the y. So what does this mean? Well, recall that with logarithms, we have the associated property that a log n is equal to log n to the a. And similarly, we have a nu p n is equal to nu p n to the a. Now, this seems like it won't do much on its own, but this is much more powerful than you think. How come? Because if that means that if x is a perfect eighth power, then nu p of x is always divisible by a for every single p. And this allows us to turn up problems about perfect powers meaning like we have perfect squares, perfect cubes, so on and so forth, into ones about simple divisibility. And we'll see an example about this at the end of the video. But for now, let's go ahead and take a look at one of our next key properties about nu p. So consider log of m plus n. There's no way to express this cleanly in terms of log m and log n. However, is the same true for nu p? For example, if we have nu p of m and nu p of n, is there a clean way to express nu p of the sum m plus n in terms of these two? Well, as it turns out, the answer is surprisingly yes. Well, sometimes. And you'll see what I mean by sometimes right now. So, property 2. We have that if nu p of m is not equal to nu p of n, then nu p of m plus n is equal to the minimum of nu p of m and nu p of n. Okay, so how on earth would we prove this? This is less obvious than the multiplication property, so let's work through the proof together. And for convenience, let's go ahead and write this value here to be a and this one to be b. And we can assume without loss of generality that a is greater than b. How come? Because if a were less than b, then we just swap these two around. So if a is less than b, we just go that way and that way. So we assume a is greater than b, then we want to prove that nu p of m plus n is equal to b as well. Now we're kind of stuck because we want to know how to prove this and get that exponent of b. And now we can try using the prime factorization. Idea of nu p. And suppose that we have m is equal to m prime times p to the power of a. Then this m prime here does not have any factors of p in it. Otherwise, they would go in here, making the nu p larger. And we can similarly write n equals n prime times p to the b. Then m plus n, if we just plug and chug, we get m prime times p to the a plus n prime times p to the b. And we want to show that this has nu p equal to b. So let's go ahead and take out the p to the b from both sides. So this becomes p to the b, so that's our exponent. Then n prime times p to the a minus b plus n prime. And we have our exponent of b here, so we want to prove that this is not divisible by p. And now we reduce it to a problem about just mod p. And because a is greater than b, this term here is just divisible by p. So mod p, this entire term here goes away. And what's left is this here. But note that by our assumption, n prime is not divisible by p. Otherwise, we would increase it some more. And this means that this entire expression here is not divisible by p. In other words, nu p of m plus n is equal to b, as we needed. Now, we could just end it here and say, memorize this fact. But the main thing I want you to get away from the above discussion is that whenever you're in doubt, so when in doubt, always take the prime power out. And this is a very important idea, and you shouldn't go around memorizing the theorem here about nu p addition and using it blindly. But rather you should know how to prove it on the spot, like here. So if you only memorize it, you won't know how to use it in practice. So go through the proof again if you need to, and to make sure that you have this solidified. And in fact, I believe so strongly that you have to have the proof known to heart that I want you to afterwards see if you know it by doing the following exercises. So exercise. So first one is show that if the new p's are equal, then we know nu p m plus n is greater than or equal to nu p of m, but we cannot say anything further. Like it could be nu p m plus 1, nu p m plus 3, so on and so forth. Then exercise number 2, go ahead and generalize the above properties. So nu p of a1 plus a2 plus all the way to plus ak is equal to the minimum of nu p of a1 all the way to nu p of ak, assuming that all of them are distinct. And finally, a third exercise regarding nu2. So if nu2 of m is equal to nu2 of n, then we actually no further prove this, then that nu2 of m plus n is greater than nu2 of m plus 1. So go ahead and prove all these on your own. And this is basically a way of me testing to make sure that you are comfortable with the proof that nu p of m plus n is the minimum of nu pm and nu pn. Now let's see how we can deal with GCDs, so GCDs and LCMs. Now, if you want to recall what a GCD is, the greatest common divisor of m and n is the largest number d such that d divides m and d divides n. Whereas the least common multiple of m and n is the largest number which is a multiple of m and a multiple of n. So these stick up to their names. Now, how do we involve them inside nu-p computations? Well, the key property is this, and nu-p of GCD of mn is equal to the minimum of nu-p of m and nu-p of n. Now, how exactly do we prove this fact? Well, suppose that p to the k divides this GCD of m and n. Then this means that p to the k divides m and p to the k divides n. And because of the definition of nu p, this requires k to be less than or equal to the nu p of m, and also k to be less than or equal to the nu p of n. And with this, by combining these two, we get k is less than or equal to nu p, or the minimum of nu p of m and nu p of n. And then with this, it is enough to prove that these two quantities are equal. You can use a very similar argument to end up showing that nu p of LCM of m and n is equal to the maximum of nu p of m and nu p of n. So the GCD gives the minimum while the LCM gives the maximum. Okay, so now let's take a look at an example of these two properties as well as the other ones we've seen in action. And the example is to prove that GCD of mn times LCM of mn is equal to m times n. Okay, so how do we prove this? Well, here comes one of the most important ways to use nu-p. Two numbers a and b are equal if and only if, and they have to be positive, they're equal if and only if nu p of a is equal to nu p of b for all primes p. So in this way, by taking the new p of both sides, where p is an arbitrary prime, this reduces to showing that new p of GCD mn LCM mn is equal to new p of mn. And now we can use the multiplication property. New p of GCD mn plus new p of LCM mn is equal to new p of m plus new p of n. And now we can just plug in the GCD and LCM formulas to get minimum of the new pm, new pn, plus the maximum of new pm, new pn is equal to their sum, new pm plus new pn. Now we can go ahead and let this one here, because this quantity shows up all the time, be A, and this one be B. So now we want to show min of AB plus max of AB is equal to A plus B. Well, now it's pretty clear why this should be the case, because one of A and B has to be the smallest one. So if this is the smallest one, this is the largest one, and therefore they add up to A plus B. Likewise, if this is the smallest one, then this is the largest one, and therefore they again add to A plus B. Therefore, we end up getting that this thing here is true, which means that this is true for all primes P. So for all P. And with this, we end up showing that these two sides are the same, and we are done. So the point is that by using new P, you can end up proving that two numbers are equal, and in this way, we ended up reducing it to a pretty intuitive fact. Now, you might notice from our intuition about logarithms is that the new P turns problems about multiplication into problems about addition, just like the logarithm. So we have multiplication to addition. And the same thing happened when we use logarithms. For example, log of 10 to the x plus y is just log of 10 to the x plus log of 10 to the y. And by using this is why the logarithm was actually invented, I think, to turn these problems about multiplication with the exponents into ones about addition and making it simpler. And the same heuristic is true for new P's. And to see why, let's go ahead and take a look at an example of this in action. Suppose we have numbers a, b, c, and d, and they're all greater than or equal to 1. They're positive integers. And suppose that ab is equal to cd. Then our goal is to prove that a equals pq, b equals rs, c equals ps, and d equals qr for some positive integers p, q, r, s greater than or equal to 1. Now, how can we prove that this is true? Well, problems about multiplication are pretty hard, so let's turn it into a problem about addition using the prime exponents. So indeed, if we let t be a prime, so t is prime, then it suffices to construct the new TP, new TQ, new TR, and new TS such that the conditions are true. And with this, we can rephrase it into the following problem. Let t be a prime, and suppose that new t of A plus new t of B is equal to new t of C plus new t of D. And prove that there exist numbers new t of P, new t of Q, new t of R, and nu t of s such that these two add up to a, or nu t of a, these two add up to nu t of b, these ones add up to nu t of c, and these ones add up to nu t of d. Now these nu t's look all scary and everything, and it convolutes our notation. So let's go ahead and rephrase it as follows. Let a plus b equals c plus d, where all of these are non-negative integers. Prove that there exists p, q, r, and s such that p plus q equals a, r plus s equals b, p plus s equals c, and q plus r is equal to t. And note how we basically turn this entire problem about multiplication into one about addition. So we're basically using logarithms, but not really. This is a logarithm for integers in a way. And fortunately, this problem is not too hard, and your homework is to prove this on your own. And this should be D, by the way. The point is that by varying this prime t, we're able to end up varying all of these numbers that we end up using, and therefore construct the numbers p, q, r, and s as we need. So the point is that you can always use nu t to break the problem down into smaller chunks, especially ones involving addition. So you can turn multiplication into addition. Okay, now let's take a look at our example problem. Which positive integers can be written of the form LCM of x and y plus LCM of y and z all over the LCM of x and z for positive integers x, y, and z? Okay, so go ahead and try out this problem on your own first and hit the pause button to try it. And when you're done trying it, hit the play button and we'll discuss it together. Okay, so hopefully you've tried the problem out by now, so let's go ahead and discuss. So the first thing we do is look at small cases. So one of them is 1, 1, 1, of course. Then this becomes 1 plus 1 over 1, which is 2. Now what if we make one of them equal to 2? Suppose z. Then this becomes LCM of 1 and 1, which is 1, plus LCM of 1 and 2, which is 2, all over LCM of 1 and 2 again, which is 2, and this gives 3 halves, unfortunately not an integer. So we might get better luck if we let this one be 2 instead, because it seemed like the issue here was that we had the 2 down here. If we could make this number down here equal to 1, then we'd be fine. So in this case, we get LCM of 1 and 2, which is 2, plus LCM of 2 and 1, which is 2, all over LCM of 1 and 1, which is 1, which is 4. And now we have that if we do 1, 1, we want to keep the denominator equal to 1, and 3, then this becomes 3 plus 3 over 1 equals 6. And in general, this makes us conjecture 2, 4, 6. The first thing we think of is all even numbers. And we can just generalize this. If we have 1, k, and 1, then this becomes k plus k over 1, which is 2k. So all evens work. And thus we need to prove that all odd numbers do not. And this very highly suggests that we look at nu2 of this entire expression. But there's a twist, because remember how we constructed the value of 3 halves? So that means that we have this 2 down here. What is the nu2 of this thing here? Because it's not an integer. And to solve that, we can do something like this. nu2 of 3 halves plus nu2 of 2 should be equal to nu2 of 3 by our property. So this is 1, this is 0, so nu2 of 3 halves is -1. And this kind of makes sense given that the 2 here is on the bottom. And we have a power of 2 right on the bottom here. Anyways, what we have so far is that the nu2 can be equal to 1, it can be 2, it can be 1 again, it can be 3, it can be basically any positive integer, because we can just set this to be any like power of 2, but besides the point. But with the 3 halves one, it can also be -1. And if the nu2 could be equal to 0, then we have an odd number, which we want to show is not possible. So therefore, we would really like to show that nu2 of LCM of xy plus LCM of yz all over LCM of yz of xz is never equal to 0. Because if it's never equal to 0, that means that we can never construct the odd numbers. Okay, so let's see what we can do with this huge nu2 expression. If we go ahead and use the nu2 rules, this becomes nu2 of LCM xy plus LCM of yz. We want to prove it's not equal to nu2 of LCM xz. And with this follows from the multiplication property of nu2. So now what can we do? Well, we have this LCM over here. So let's go ahead and write this out as the maximum of nu2 of x and nu2 of z. And before we get into any trouble, it looks like we're going to keep using nu2 of x, nu2 of z, and also the nu2 of y over there. So let's go ahead and create variables for those so that we don't get confused and save ourselves trouble. A is equal to nu2 of x, b is equal to nu2 of y, c is equal to nu2 of z. So then this here becomes max of a and c. Okay, that's one side of the equation down. And now we have the other one to go. So what can go wrong here? Well, we want to somehow use our nu2 addition property, the one I discussed earlier. However, there's a catch we have to consider, and it is that nu2 of LCM xy is not equal to nu2 LCM of yz, as otherwise the addition formula is not true. So let's go ahead and assume that this is the case for now. If we go ahead and write this in terms of ABC, this translates to max of AB is not equal to max of BC. Then what this becomes is min of the max of AB and max of BC is not equal to the max of AC. And we want to prove this given this here. And now we just take lots of cases on what these maximums and minimums are. So if the minimum here is B, the maximum here is B, and the maximum here is B, then this means that B here must be equal to, if we're assuming a contradiction, let's suppose that we found these magical values of A and C, then this means that B here is equal to the maximum of A and C. And suppose that we have A equals B. So we have A equals B, and then we have B is greater than or equal to C. Then this means that this here is B, and this is B, and they are equal. And that contradicts our assumption. So therefore, both of these maxima can't be B. What if one of them is B and one of them is C? Then this means that, well, A is less than or equal to B is less than or equal to C, so which means the minimum is equal to B, and the maximum of these two is C. But then these two are equal, so are these two here, and that's bad. And something similar happens if we use A, and if this minimum here is A, and this one here is B. And then there's a final case where this is C instead. And that means that A and C are both greater than or equal to B. And so minimum of A and C is equal to max of AC. But this requires A equals C, because if the minimum equals the maximum, then clearly the two numbers must be equal. But then this is A and this is C, as we said earlier, and that doesn't work. So therefore, we have gone through all the cases and figured out that minimum of max AB, max BC cannot be equal to this, given that this here holds. And obviously now the question is, what if this does hold? What if maximum AB is equal to maximum BC? Then how do we deal with the left-hand side? Well, we can't really say much about this, but what we do know is that from our exercise I gave earlier about nu2, this is at least equal to the max AB plus 1. And notice the plus 1 here, because we are working with nu2. This is what makes nu2 so special, and this is probably going to be the key to solving the problem. And because note that we never used any specific facts about nu2 until this one here. Anyhow, suppose that we have that max is equal to this and is greater than or equal to that. So max of AC is greater than or equal to max of AB plus 1, which is also max of BC plus 1. And now we can just take cases on the order of A, B, C. So if both of these maxima here are equal to B, so this is B and B, then that means that we have one of A or C is greater than or equal to B plus 1. But then this means that A and C both exceed the maximum, making the maximum not equal to B. Because if, for example, if A was equal to B plus 1, this would be B plus 1 and B, and that would make the maximum B plus 1 instead of the B here. Okay, so both of the maxima being B doesn't work. What if one maximum is B and the other is A? Then this means that A is less than or equal to B, or A is greater than or equal to B, my bad. And then B is greater than or equal to C. And this means that this maximum here is equal to A. So A is greater than or equal to A plus 1, which is bad. We obviously know that's not true. So we can't have that's the case. And you can similarly determine that if this is B, this is C, then A is less than or equal to B is less than or equal to C, and then therefore C is greater than or equal to C plus 1, again doesn't work. And the final case we have to consider is where this one is A and the other one is C. Then B is greater than or equal to both A and C, and therefore max of A and C is greater than or equal to the A plus 1 and C plus 1. But if this maximum here was supposed A here, then this means A is greater than or equal to A plus 1, which is bad. And if this maximum here is C, then this means C is greater than or equal to C plus 1, and that is bad as well. Therefore, in all cases, by using this plus 1 over here that's unique to nu2, we arrived at a contradiction. In both cases, where the nu2 of this was the same as this one here, or in the case where they were different. So this proves that the nu2 of this expression here can never be equal to 0, and this implies that the expression, if it's a positive integer, must be even. And we have this construction over here. The reason why I like this problem a lot is because it tests your knowledge of nu2 and nu-p operations. And it also requires you to make note of the fact that nu2 has a special property where you have the plus 1 and plus 1 here. And that gives us the solution to the problem. So go ahead and go through this proof as many times as you need to in order to get comfortable with it. Because if you know exactly how this proof works, then I can guarantee you you're very solid with nu-p operations. So thank you so much for watching this video. Please subscribe to see more videos, and I'll see you guys in the next video.